Welcome to lesson 6, where we're going to talk about some common discrete distributions. So what we did is we got into the general flow of it, like if you have a discrete random variable, here's how you can take the probability mass function and find the expected value and find the variance and the standard deviation. Well, in some cases, we have special or common distributions that we know, hey, this is what the expected value will be time and time again. This is what the variance will be time and time again. And the binomial distribution is one of those. It's a very, very commonly used distribution. So just to list a few that are really common. So there's the Bernoulli random variable. So this is almost the equivalent of flipping a coin one time. So there's a probability of success. Let's say the probability of heads is 50%. And you flip the coin once. You either get heads or you don't get heads. That's the idea. So it only has two possible outcomes, and it's one trial. Binomial is that special case where it's multiple Bernoulli trials. So maybe I have a coin and I flip it 10 times and record the number of heads I get out of those 10 flips. So you have a set number of trials, so 10 flips, and then a set probability of success. So if I'm using a fair coin, it'll be 50% probability of heads for each flip. And then my random variable x would be the number of heads. Geometric, you could look at modeling the number of trials until your first success. So if I'm still into coin flipping, which honestly, in statistics and probability, we like flipping coins and rolling dice and drawing cards a lot, and I'm sorry. So this would be the idea of flipping a coin until you get a head. So you have to flip it at least once, but you could flip it forever and ever and ever, and never get a heads. Probably not realistically, but you could. So it could be 1, 2, 3, 4, 5, and so on. It doesn't have a limit. Like the binomial, you have a set number of trials. The negative binomial, this is related to that geometric, so maybe I want to know how many times I need to flip a coin until I get 5 heads, some number other than 1. And then Poisson, this is looking at counts, so in a specific period of time or interval, how many observations of interest did I observe? A lot of times people will use these for like Q, when people are in line, like, oh, how many people might we expect to come into the store? How many defective parts might we expect on one particular product? That kind of idea. So we're going to go through the binomial, and then lesson 7 is going to touch on the Poisson. Just know that there are a number of them out there. These are just well-known discrete random variables we'll use a lot. So the binomial, it models the number of successful outcomes, so it depends on what you determine what a success is. If you're flipping a coin, you can say success is getting heads. You could also decide that it's getting tails. Depends on what you define as success. Out of n Bernoulli trials. So you have a certain number of trials. If you're flipping coins, this is how many times you flip the coin with a probability of success p. So that probability of success shouldn't change from trial to trial, and that's why we like to use coin flips a lot, because from coin flip to coin flip, the probability of heads shouldn't change. So definitely super important that you have n independent Bernoulli trials, and you define what is a success versus what is a failure. So there's success and then everything else is a failure. So, and that probability of getting a success will be p. So a really, really common one would be, suppose I want to flip 3 coins and x is the number of times we flip a heads. That random variable x, the number of heads, is binomially distributed. So x can be 0, I can get 0 heads out of 3 coin flips. I can get exactly 1, exactly 2, and exactly 3. And if, as long as the probability is the same for heads for all 3 coins, it's going to be a binomial. Okay, so when we have the binomial distribution, we can go ahead and we know the number of trials it's set. The probability of success is P. We can set up the probability mass function. So X is the number of successes out of n trials. So it'll be n choose X, and we'll go over this notation here, times P to the X. So if you think about it, it's X successes. 1 minus P to the n minus X, so you have n minus X failures. And X can be equal to 0, 1, 2, all the way up to n, whatever your number of trials is. So looking at that notation, n choose X, I want to be really careful because n choose X, it's in parentheses, but notice there's nothing in between. It is not equal to n over X. It is not equal. This is its own thing. Want to be really, really careful here. So n choose X, it's saying, okay, well, how many different ways could I pick exactly 2 coins out of 3 flips as heads? It helps us find, all the permutations there, like how many different ways could that happen? So you'll have n factorial over x factorial and n minus x factorial. So note if you added these 2 numbers here on the bottom, so x and n minus x, you'd get n. And then a reminder there, so factorial, it's that exclamation point that we're using here. And the idea is we use factorials for integer values, specifically non-negative integer values. And it would be like, so 5 factorial, it would be equal to 5 times 4 times 3 times 2 times 1. So it's essentially a countdown. It's the number times 1 minus 1 less than that times 1 less than that until you get to 1, and then you stop. So that is important to note. Other special cases here, 1 factorial is equal to 1. 0 factorial is also equal to 1. If it weren't equal to 1, if it were equal to 0, that would be super problematic. Just know that 0 factorial is equal to 1. It's a special case. So we would have that up. Now this notation here kind of will explain how we set up our PMF. So things that are cool, it still would be, if we wanted our expected value of x, it still would be from x equals 0 all the way up to n. And it would still be x times, and then n choose x, 1 minus p, p, x, 1 minus p, n minus x. This would still how we get our expected value. But thanks to, somebody did a lot of the math, and I could post the math too if you would like. You can show that every time you do this expected value for a binomial PMF, you end up getting n times p. Similarly, when you go ahead and you find the variance for this PMF, it always is going to come out to n times p times 1 minus p. So you absolutely could go ahead and find the expected value of x squared and go ahead and do all the math, and that's totally welcome. Just know that it will always come out to n times p times 1 minus p if you're using a binomial PMF. So now we're going to work through an example. So we have a 20 question quiz, and it's a pop quiz. The student's totally unprepared. Every single question it's a multiple choice question with 4 questions. So what they do is they just guess at random for all 20 questions. Hopefully this is not a realistic scenario. We're just kind of playing here. And x is going to be the number of questions answered correctly. So x could be equal to 0, 1, 2, all the way through 20. They could randomly guess all of them correct. But since these are all strictly multiple choice, they can't have like 2.5 correct, right? It has to be 0 through 20 and only integer values. So the probability here that they guess correctly is going to be 1/4 because they're just guessing at random. So each single question of these 20 questions is its own Bernoulli trial. So question 1, did they get it right or wrong? Question 2, did they get it right or wrong? All the way through question 20. So what are my parameter values for the distribution? So I want n and I want p. So I want to know the number of trials, or in this case, the number of questions. So there are 20 questions. It's a fixed number. And p is saying, okay, well, for each question, what's the probability of success? Since you're randomly guessing from 4 choices, it's going to be 1/4. So what is the probability mass function of f? So my probability mass function, so it's n, choose x, p x, 1 minus p, n minus x, which I am going to plug in values here. So 20, choose x, times 1/4 to the x times 1 minus 1/4, it's just going to be 3/4. You are welcome to put decimals if you like. I'm just going to leave this for now. So then 20 minus x. So for x equal to 0, 1, ... through 20. And this is going to be 0 anytime else, right? So this PMF is equal to 0 for any time that x is not equal to 0, 1, 2, 3, 4 through 20. Oops. Wrote there a little bit. So how many questions should the student expect to get correct? On average, it's asking us for the average. So if a student went ahead and guessed at random for all 20 questions, how many would we expect them to get correct? And a lot of y'all will have the correct intuition here. You'll think, oh, if there's 20 of them and I have a 1/4 probability of guessing right, it's going to be 1/4 of 20 or 5. But if you want to write it out, so my expected value is just going to be n times p. So you're right, 20 times 1/4 is going to be 5. So on average, a student that randomly is guessing their answers on this multiple choice quiz for all 20 questions, we would expect on average them to get about 5 correct. And then what is my standard deviation? So here we're going to go ahead and do what we did before. We're going to calculate the variance and then square root. So my variance of x is np times 1 minus p. So I can go ahead and I can plug in. So it's going to be 20 times 1/4 times 3/4. So it's going to be 60 over 16. You could do math here. 4 goes into both. Something over 4. 15 over 4. So it's going to be 3.75. I believe here. So now if I want the standard deviation for x, I need to square root. So that is one thing that's super useful pretty much in any math course or stats course that I find myself going on side quests. I'd go, aha, here's an answer. It is an answer, but it's not the one we're looking for. We're looking for the standard deviation. So just try and remember, okay, did I answer the question? That's an excellent question to ask yourself. Once you get to some solution, you're like, hey, did I answer the question? So not quite. I'm going to just square root it now. So square root 3.75. And I'm going to get, I'm going to round a little bit, 1.936. So if we had students guessing at random for these 20 questions, we'd expect on average for them to get about 5 correct, and to vary on average about 1.936 questions correct. Not very high if you're guessing at random, but in general we kind of encourage you to try and you know, reduce the options if you can. Hopefully not a realistic exam taking method. Some more questions. So now we want to know how likely is it the student will get exactly 10 questions correct. So they have 20, they randomly guess all of them, and we want to know the probability they get exactly 10. So probability x is equal to 10. So now I'm going to plug 10 in for x into my PMF. So 10 choose 20, 20 choose 10, times 1/4 to the 10th, times 3/4 to the 20 minus 10, so 10. So if I want to break this out, so this will be 20 factorial over 10 factorial over 20 minus 10, which will be 10 factorial. So 1/4 times to the 10th times 3/4 to the 10th. Honestly, I strongly recommend, if you're not using a calculator, R is an excellent resource for doing this math. This is not do in your head math most of the time. It could definitely be easy to become overwhelmed keeping track of everything. So, I mean, one thing that's nice too is, so this would be 20 times 19 times 18 times ... times 11 times 10 factorial. You have 10 factorial over 10 times 10 factorial. One of the 10 factorials would cancel out. But still, that is a lot of math to plug into your calculator. Know that if you wanted to use factorial in R, you would write factorial and then like 20, like that, and it would do it for you. In a calculator, I believe there's a function for factorial as well. Just know you don't have to write 20 times 19 times 18 times. It will take several lines to do if you want to do it that way. So I end up getting, after doing the math, 0.0099. So what this comes down to is if you have 20 questions and you randomly guess and there's a 1/4 chance of getting it correct, less than 1% of the time you would expect to get exactly 10 of them correct. That's what this is saying. So then we have another there. So less than 20% of the questions correct. So this is one of those times you want to make sure you pay very careful attention. So we are saying probability that x is less than, so 20% of 20, so 1/5 of 20 is 4. They are not saying 20% or less, or 20% or fewer. They're saying less than. So we want to know that it's less than 4. And I just am noting this is not equal to the probability that x is less than or equal to 4. In the discrete case, these two things will not be equal to each other. So be very careful. So I can go ahead and I can rewrite this as probability x is equal to less than or equal to 3. So probability x is equal to 0 plus the probability it's equal to 1. Probability is equal to 2 plus the probability it's equal to 3. I strongly recommend taking a look at the R code that we provided for the discrete distributions for the binomial. It is included in the last few slides in the PowerPoint. Just know that this is a lot to do by calculator. It is very, very easy to do in R. But if I want to set it up, I'm going to give myself a little more room. It's going to be equal to 20, choose 0. So I have to set up the PMF for each one of these. So 20, choose 0. So 1/4 to the 0, 3/4 to 20 minus 0, plus 20, choose 1. That's just going to be 20. 1/4 to the 1, 3/4. It's going to be 19. 20 minus 1. Just note that these, in each separate probability there, those exponents will always add to n whatever n is. So it's 20 here. And just keep going. 20, choose 2, 1/4 to 2, 3/4 to the 18th, because you have 18 failures if you have 2 successes. And then last one here, 20, choose 3, 1/4 to the 3, you have 3 successes, 3/4 to the 17th, because you have 17 failures. So this would be my setup here. Let me see, I think I even have numbers here. So that's going to come out to, I'm sorry, I have a tendency to not speak a lot while I'm writing, or I totally goof it up. You feel free to take a pause, check this math. Definitely allow yourself the chance to do this math before you watch me do it. It definitely helps. But absolutely do what will help you the most here. So plus 0.669 plus 0.1339. So those are my 4 probabilities. I add them together. I'll get 0.2252. So what this comes out to is the probability that I have 20 test questions or quiz questions, and I have a 1/4 probability of getting each right because I'm randomly guessing my answer. The probability that I get 3 or fewer correct, or less than 20% correct, happens about 22.52% of the time, given the parameters that I have 20 questions and the probability of getting each one correct is 1/4. So fairly common. Definitely more common than getting exactly 10 correct. Definitely. So that'll be our little spiel on binomial. So just know that binomial, discrete random distributions, they're just a specific set where you have a set number of trials. You're looking at successes and failures, usually counting the number of successes, and you have a set probability for success for each trial. That will be our binomial, and we'll get to the Poisson distribution in lesson 7.